Applying first principles. So we just discovered our first principle formula, and which finds us a gradient of a tangent at any given point. And here we're going to apply it to a function. So we want to apply the first principle formula to f of x equals x squared. And our first principle formula helps us find the gradient of a tangent, and the formula is the limit as h approaches 0 of the f of x plus h minus f of x over h. So let's look at how we can use this. So f of x we know the f of x is x squared. So what we want to find is the f of x plus h. So the f of x plus h, we can see that we just want to replace, anywhere we see an x, we want to replace it with the bracket and x plus h. So there's an x right here, so let's replace it with an x plus h, and it's squared. So all we've done is replace an x with a bracket and x plus h. Let's expand this out. So we'll square our first term to get x squared, double the product of the two terms, so it'll be 2hx, plus square the second term, so we get h squared. And that becomes our f of x plus h. So now we can apply our first principle formula, where the gradient of the tangent equals the limit as h approaches 0 of our f of x plus h, which is x squared plus 2hx plus h squared, minus our f of x, which is x squared. You'll notice I put a bracket around it. In this case it didn't matter because I only had one term, but when you have multiple terms for your f of x, it's important to include in a bracket because we'd have to subtract every term. All of that will be on h. So now we can start simplifying it. We have the limit as h approaches 0. Now x squared minus x squared will cancel out. So we're just left with 2hx plus h squared over h. Now in the numerator, we can factorize out a h. So we'll have 2x plus h all over h. These h's will cancel out. So we're just left with the limit as h approaches 0 of 2x plus h. Now that h is not in the denominator, we can now see what happens as h approaches 0. As h approaches 0, this value of h will approach 0. So all we're going to have left is 2x. So basically we're trying to simplify as much as we can until we get rid of the h in the denominator, so we can then sub h equals 0 to find our limit of the function. And remember, this equals the gradient of the tangent. And this is one of the most important definitions in calculus, where when we apply our first principle formula, we're actually finding the gradient of the tangent at any point on the curve. So let's look geometrically what this means. So let's look at our original function of f of x equals x squared. And what we found is that the gradient of the tangent at any point is equal to 2x. So let's look at a point. Let's look at x equals 1. If we drew a tangent here, what is the gradient of that tangent? Well, we can use our gradient function to find this, because this defines the gradient of the tangent at any point. If we want to know specifically what happens when x equals 1, all we have to do is sub x equals 1 in here. So let's do that. Gradient of the tangent at x equals 1, 2 times 1 is 2. And what it's saying is the gradient of this line will be 2. Let's look at minus 2. Let's draw a tangent there. What's the gradient of that line? Well, we can use our gradient function of 2x And we want to know what happens when what's the gradient when x equals minus 2? So we can just sub in minus 2. 2 times minus 2 is minus 4. And what this means is the gradient of this line is minus 4. And we can do that for any point on this parabola. Let's do one more. Let's look at the vertex. If we drew a tangent at the vertex, we get a horizontal line. And we should all know that the gradient of the horizontal line is 0, but let's double check, because that's when x equals 0. We know the gradient of the tangent equals 2x. So when x equals 0, we get 2 times 0, which is 0, which makes perfect sense because the line is horizontal. So remember, whatever value you get, whatever function you get for the gradient applying first principle, that will define the gradient of the tangent at any point for x on the function.